To it. Today's program is non-destructive and destructive test methods to evaluate existing masonry structures. Here is a program description and the learning objectives today. Also the continuing education, you'll receive 1.0 development hours and 1.0 AIA learning unit, health, safety, welfare. Here's our provider statement for AIA credit. We also will have certificates given after the seminar, and I've been sending them right after the seminar. However, if you need a year in, just give me a holler and I'll send your year in to you as well. And look for the evaluations after the program in an email. We also have today some giveaways. We have 2 pocket guide construction, brick construction, and we also have not the person, but we have the nice Carhartt jacket, compliments of the Mason Contractors Association. They're chartered in 1896. The Mason Contractors Association of St. Louis is one of the area's oldest construction industry trade. Place your business card. There's going to be a little plastic box coming around, and hopefully we'll get you all cozied up in that. Our sponsor today is John J. Smith Masonry. And we do have Brian Smith up here at the bar. Thank you so much for the goodies and refreshments. We appreciate it. So John J. Smith Masonry, across 3 generations, John J. Smith Masonry has earned a reputation for their outstanding craftsmanship with dedication to safety. They have their footprint on the St. Louis area and elsewhere all over the Midwest. They have earned numerous awards and recognition in St. Louis, as well as across the nation. Trust your most important masonry work to Smith Masonry, a family company with a long history of excellence. Thank you again, Brian. And today's speaker is Stephen Fults, PE, with Special Inspections and Design. He received his education, graduate of Civil Engineering, Structural Emphasis, SIUE Edwardsville, and non-destructive testing NDT certificate from Spartan School, Tulsa, Oklahoma. He has many national certifications and his work experience. He is co-owner and principal engineer of Special Inspections and Design with offices in Chesterfield, Missouri, and Collinsville, Illinois. So please give Stephen Fults a warm welcome.
Thank you. It's a pleasure to be here. My first time as a speaker. I've been here as a participant a lot of times. So today we're going to talk on non-destructive testing of existing masonry structures. The handout that you have is very close to the presentation I'm going to give, but some of the pictures, the presentation has some kind of stock cartoon pictures, and we replaced those with actual field pictures. So to start off, I'd like to say that as design professionals, we rely on numbers, right? And some of the most important numbers, they represent the design load on a structure during an event times a certain probability of the event occurring, a safety factor. And that's compared with the resistance of the structure. And so this is the historical stress versus strength comparison. And so the resistance of a structure is based on its geometry, the efficiency of the connections, and its material properties. So the geometry is pretty straightforward to get. Connections have to be analyzed, but the big unknown is material properties. And because when we deal with century-old masonry buildings, they have no design, often have no design drawings. They've gone through multiple modifications. So investigation and testing of the actual structure, this gives the most accurate values to base your design. And so the goal of this presentation is to identify techniques used to measure material properties to take the unknown out of the resistance of the structure, to eliminate, or to, instead of having assumptions, is actually to assign a qualitative, quantitative number of value to the property needed for your design. So the material properties that that we achieve through these testing are compressive strength, shear strength, diagonal tensile strength, modulus of rupture and elasticity, bond strength, and the in-situ shear stress, because we can measure the amount of dead load on a particular structure. And so how to sample, where to get the data is through destructive or non-destructive means. And so in a destructive mean, it was actually to go to the structure, remove samples, transport them back to a testing laboratory, test in the laboratory, and then patch the material. So that's frequently done. Another technique is to test the materials in place with localized destructive techniques. For on the non-destructive aspect, so we can conduct a field proof load test, and like if you a load test would normally you would test it to failure, but a proof load test we test it to an established, like the structural engineer will give a value that we would take it there and then stop the test, and so it would become, it's a non-destructive test in a sense, because we would stop the test before we would reach the elastic limit. The other one is to perform a non-destructive testing of the in-place in-situ materials. So our presentation, what we're going to go through just some common masonry nomenclature, so we're all on the same page with some of the terms I'm using. We'll go through some laboratory tests. Those are the removed samples, some destructive tests, some load test examples, some non-destructive testing techniques, and then some demolition examples of structures our company was involved with that were beyond their useful life and were demolished. So start off the major components of reinforced concrete, reinforced masonry. So we start with a CMU block or brick, mortar, reinforcing steel, grout, and skilled masons. And so I do have to say that we are blessed in the St. Louis area of having very good skilled labor. The masons are incredible. And I really think, looking at the structures in the Central West End, down on the Cleves Landing, Washington Avenue, Couples Complex, we all been involved in a lot of those projects. And the level of construction is very high. It's the problem that without the maintenance, you let water infiltrate, that's when the deterioration begins. But the initial construction, I believe, was very high quality. So to start off with the basic, the CMU, the concrete masonry unit, these are established, meticulously manufactured concrete block that are governed by ASTM C140 for their dimensions, compressive strength, absorption rate, density, to name a few. There's a longer list. And so these are established materials. Numbers are in the design guides, and you can count on them. Very, very few unknowns. Some brick masonry terms. So I'll be talking about head joints and bed joints. Bed joints are the horizontal surface. Running bond is the most frequently used. Stack bond is more architecturally pleasing, has less flexural strength. And then the mortar joint finishes, these are different options. And so a tooled mortar joint has good moisture resistance. On reinforcing steel bars, they're sized by 1/8 increments. So a number 3 bar is 3/8 inch diameter. A 5/8 bar is a number 5 bar. So when all steel, it's a known quantity. When it arrives at the job site, it's going to be tagged with its ASTM specification, its classification and grade, and then the bar size. Okay, so the next component, mortar. So a lot of mortar today is pre-blended. It's pre-approved by proportion. So it's an assumed, or it is an approved mix design. It arrives in bags. They put it in silos, and so the masons, the mortar, it's constructed of Portland cement, hydrated lime, fine sand, water that is added by the mixing crew to the consistency they need for that particular day and the environmental conditions that they're in. So it's mixed for 3 to 5 minutes in a paddle drum mixer, transported to the masons in a lull, and then construction begins. The max time is 2.5 hours. You can have mortar on a board. It can be retempered once with water. Some facts about mortar is that, so bond strength is more important than high strength. High strength mortar, it lacks ductility, it's brittle, it will not flex, it'll crack before flexing. And so a lean mortar has better bond and is what is more desirable. And so when you're tuck pointing, if you use a very stiff mortar for tuck pointing, it actually puts more stress concentration on the face of the wall and can lead to face cracking of the brick because it's stronger at the face than it is in the rest of the bed joint. So grout bonds the steel to CMU block. So grout is placed very wet, soupy, like a 10 to 11 inch slump. And the reason for that is you need the grout is pumped or into the block, into the open cells, and the block is dry, and so the block absorbs the moisture out of the wet grout. And so that's the bond strength. It's actually created by the fluid pressures and the absorption that, like little cementitious tentacles of the grout, actually enter the microscopic pores of the CMU block, and it's kind of like a weld that has good bond strength, and that's necessary. So it creates a composite material similar to reinforced concrete. So you've got block, grout, and rebar. That's just one. So there's 2 techniques for grouting. This is for vertical grouting. And the specifications will say it's either got to be a fully grouted wall, grouted on 16 inches, 32 inches, whatever. So it'll be specified. And so there's low lift grouting, which is kind of preferred, and it's limit 5 feet. And so normally it's done at a bond beam and below, and then you build up, and then you would you would actually grout. The grouting for a level, it's a continuous operation, and you still have to puddle or vibrate the grout in the cells. So the other option is a high lift grouting, so you can actually go 12 foot 8 inches, but vibration is supposed to vibrate twice. And to do that, you need a vibrator that's 13 foot long to get to the bottom. It's a more difficult operation. Cleanouts are required. A cleanout is a knockout in the bottom. They cut out a section of the CMU block. So during the grouting operations, you can actually verify that it was efficient and the grout got all the way through to the bottom. Then you plug it back up. Another critical element, the horizontal bond beam. Again, it's a U-shaped block. It's continuous horizontal steel bars. Lap splice is critical. Typically, these are every 4 foot vertically. And so what the picture on the left shows is the grid work of the vertical grouted cells, horizontal bond beams, and so this is what provides the wind and seismic resistance of your wall. The shear stress is transferred to the steel through the bond strength between the block, grout, and steel. And so what I've read during this is that a reinforced wall has approximately 50% greater diagonal tensile strength than an unreinforced wall. So last type of reinforcement we'll talk about is the horizontal joint reinforcement. It's like ladder type. It's normally every other course. And so this is the horizontal ladder reinforcement. It's to combat the more smaller movements in a wall. When the sun hits a wall, it grows, and at night it cools, and so that the wall is always going through small temperature changes, and so the horizontal reinforcement, it's there to absorb the shear stress after the wall cracks, because masonry is stiff, reinforcing is ductile. As the movements occur, there you actually get micro cracks that begin in a wall, and then once the force is transferred to the shear steel, it reduces a crack width. I will cover some laboratory testing techniques here. And just a quick note on, I'm going to show how to test mortar and grout in field testing, but a lot of times, so field testing of mortar and grout is not done, it's not required that often. It's kind of been eliminated from a lot of specifications, but instead of that, you specify by proportion. And what that means is there's actually in C270, there's for mortar, there is approved mixed designs. Through empirical data, it's kind of like approved concrete mixed designs, there's approved mortar mixed designs, there's approved grout mixed designs. And so if you select these proportions, you buy the pre-blended mixture, have silo, you do not have to make the test samples. You still have to do inspections, but the test samples would not be required. The other alternative, the older way that was specified is specifying by properties, which is by testing. And so you would actually use field tests to verify the strength of the materials, but I have a few slides to show why that's really not so good, because like on mortar strength, a cube, when you make a cube, you have a 2 by 2 by 2 block. It was made in a non-absorptive mold, and so it's tall and square. If you compare the compressive strength of that sample versus a bed joints are low, wide, and have greater compressive strength. I jump back to this one. So this is a procedure how a cube mold would be made. Start a brass or plastic mold. You make them in the field, you leave them undisturbed for 48 hours. Bring them back to lab, cure them for 7 to 28 days, and then test it. But the problem is, because the mold is non-absorptive, and it may be at least 30% weaker than actually the field strength. So with grout specimens, here's another technique. So there's two ways that you can make field grout samples. And it's covered by ASTM 1019. So the two pictures on the right, it's a pinwheel configuration. So you actually use CMU block in the field. You configure them so the space in the middle is a 4 by 4 by 8 inch. You fill that with grout, you rot a specified manner. You leave it for 48 hours undisturbed. Bring it back to the laboratory, cure it for 7 to 28 days, and do a compression test. And that's a pretty good test. Also, you can use a grout box, same thing, but it's cardboard, it's absorptive, So it simulates field conditions. But again, so if the specification for grout is not over 2,000 PSI, this testing is normally not required. The third way, and what I feel is the most accurate way to predict the compressive strength of field condition, is to create a prism. And these are made by masons using the same materials as in the field. So you use the same block, same mortar, some grout. So you would actually make a prism, a stacked test sample. You leave it in the field. These can be made in the laboratory also. They stay undisturbed for 48 hours. You cure them for 728 days, and you do a compression test. And so that's called the unit strength method. And so this, in conjunction with specifications by proportion, is what I feel is the most accurate way to have a good grip on the compressive strength of field conditions. Another test to determine the flexural strength of concrete. This is our masonry. This is how a wall would perform under high wind conditions, is a wrench bond test. Again, the masons will make a prism. It's put in this fixture in a laboratory sense, and you measure the torque to wrench away, to tear off one brick from the brick below it. And you get that force can determine the flexural strength of your mortar joint. You move it up, test the next one. You move it up, test the next one. There is a torque wrench application for field that I'll show on a slide later. So another test, this is a shear wall mock-up. And so shear walls they're induced with vertical axial loads and lateral in-plane loads, and they create diagonal tension. And since masonry is an anisotropic material, meaning it behaves differently depending on the direction of the load. And so this particular test, these are older tests. There's been empirical data. This is not a frequent test, but enough has been done that these type of laboratory tests over the last 30, 40 years, they make the design values in the manuals we use. And so this is a diagonal tension induced through a compression load, and it shows that the maximum strength of masonry is at 45 degrees. Masonry is weak in tension, strong in compression. It will cover some destructive in-place test methods. This is what we're going to talk about. The first one we'll talk about is core samples. So this is taking a core drill out of a masonry wall. Cores are cut with a diamond-tipped wet core bit. The core rig for wall, it's anchored, it's bolted to a masonry wall. If it's a concrete wall, it can be vacuumed onto a wall. So you can learn a lot from a core. You can determine the quality of the bond strength. You can look for voids. You can do a compression test on it. You can do a tension test on it. For masonry, there's ASTM standard requires an 8-inch diameter core. And so you can actually get that core and rotate it and break it in different directions so you can determine the diagonal shear stress. Another test is it's the shove test, the shear strength test using hydraulics. This is a building downtown. It's a Tums building just east of the baseball stadium. A local engineering firm did a complete seismic upgrade on Tums building, which, Tums could have moved out to Wentzville and built a pre-engineered metal building, did everything they did, but they chose to stay downtown. And so the Tums building has like 5 different buildings they went on, and masonry is different in every one of them. And so we did a series of tests We're the testing firm for a local engineering firm, and so we tested like 6 areas in each building and got some very good data, very interesting data. So this is the test that you put you remove 2 bricks. So the brick in the middle is like number 713. That's the test brick, right? So you remove 2 bricks behind it and a brick in front of the test. You put in a hydraulic ram that's calibrated system with a load cell, and on the right side of it, you have a dial indicator that measures movement. And so as you pump your system, you apply force to the side of that brick. You're trying to push that brick sideways. And what's resisting it is the bond strength of your bed joints. So here's a test underway. You push it, and first movement is failure. And so you can determine the shear strength by your horizontal force divided by your bed joint slip planes, which like on a brick, it's about 30 inches square top and bottom. And then you have to consider the amount of axial load up above, because if you have a great deal of weight on it, it's actually going to increase your shear resistance. So you take all that into account, and so you can achieve the shear strength. So you're not assuming this in your design loads. It's actually give you quantitative, accurate information. So this is an appropriate test for older masonry that has weak mortar. You wouldn't do it on a new, it's not really appropriate for new construction. This is for old construction. So here's one example that this is down at Tum's building. It's very near the baseball stadium by the loading dock. So we were testing the block in the middle where the vertical black arrow is. And so we got our ram on the right, pushing to the left. We got our dial indicator on the left, waiting for movement. So we put over 19,000 pounds on that brick, and it didn't move. But what happened, the back of the wall blew out, because it shows that we should have scooted the test over and done it and had more of a heavier buttress behind it. So this just shows that the shear stress of that center brick was greater than the tensile capacity of the wall. So again, this is a localized destructive test. I kind of figure like I won on this one. So it tore off, masons rebuilt it up. So when you walk by, you can actually see the new masonry in there. All right, so some more testing from the Tum building. This is using the flat jack test. So this is a test that measures the in-situ compressive strength of existing masonry. And so it uses, this is a flat jack. This is one of them right here. It's an expandable steel envelope bladder. And so, let me go to the next picture. All right, so here's the test setup. And so you would actually, the first thing you do, you install 4 gauge points in between the areas. So your test area is, it's like 5 courses high. So you install these gauge points, and that's for your strain measurement. So you know exactly how wide they are. And then you take a circular saw, and you cut out the mortar joint above it, mortar joint below it, and you slip this hydraulic jack inside the mortar joint, and it's a tight fit. So then when you start pumping your jack, and so it expands, and so it's actually inducing a force up and down, but since you got 2 of them scissored together, you're actually squeezing, implying a compressive stress between the jacks. And so the load cell, or PSI gauge, it measures your applied force. You have a strain gauge, and so as you're loading it, and you see we're always holding it like this, because you really don't know what's going to happen. So as you apply force, you're actually squeezing the brick. And so from that, you can determine your load, your stress strain curve from your load displacement relationships. So there's 3 mechanisms are three techniques that we use with this. One of them is to measure the compression strength, kind of like what we did on this test here where we took it to failure. The second one is to determine like the compressive modulus, the stiffness of the wall. You don't take it to failure, but you stop before that, and you would do repeated tests at different force levels. And sometimes we can't, our system maxes out before it cracks. And so in that case, we go to technique 2, you do repeated tests, and so you can get enough data to draw the curves you need. The third one is actually to use a single jack, single bladder. So you grind out one mortar joint, you insert your flat jack, and then you put a gauge point above and below, and so you start pumping it up, and so it spreads out, and so you actually lift the wall up above. And so when it moves, as that bed joint opens up, you stop the test, and then you bring it back down. But you can actually measure the amount of axial force in that area of the wall. So here's an example of the field wrench bond test, again, where you would remove, the picture on the right shows you remove enough block where you can clamp onto one brick, you cut out the head joint on both sides of it, you put a torque wrench on there, and you measure the force to wrench that top brick out. And that'll give you the flexural strength of that bond joint. All right, so here's an example. Is that wall CMU reinforced? So this is dealing more with new construction, but I know we've been taxed with this, where if we're asked to do a condition survey on a building or due diligence on a real estate sale or something, is if someone's going to pay $3 million for a new building, they're like, well, is this building reinforced? You don't know. It's painted well, it looks pretty. The drawings might say it was grouted, if there's drawings, but they're not even drawings. So it's a guess. If I'm going to spend that much money, I'd want a reinforced building. So I kind of came up with it's the 5 pilot hole test. And so you take a hammer drill with a 3/8 masonry drill bit, you drill a hole through the face of a block in the center of the cell. If you hit resistance, it's grouted. And then plus the powder will change. As you're drilling through, the block will give you one color powder. As soon as you hit the grout, the powder changes. So you're in grout. That doesn't guarantee there's steel in there, but you hope if they grout it, they put steel in it. But there's a technique later on. I'll show you how you find reinforcing steel. So anyway, you drill your first hole, and then you go and you drill 5 successive holes. And if you get to 5 cells, and every one of them is empty, if you're drilling and it just boom, punches in, it's empty. If you do 5 of them in a row, chances are it's not grouted. You should probably go then to like your door frames or your window sills and see if they grouted those. And those should be grouted, reinforced. But not to say that a hollow walls do have some advantages, because they're not as strong, but they have better sound resistance. They have better thermal properties. They don't conduct heat as much. So then this test, this 5 hole, you would do this on the inside. Don't do it on the outside. But then you patch the holes. You can buy a tube of grout and patch all those up and close it. No one would know you're there. So another inexpensive test to determine is there horizontal joint reinforcement. So this is we bought this metal detector at Lowe's for $160, and it will find joint reinforcement, because joint reinforcement is only about 3/8 of an inch from the surface. So it's important to know, is it on 16-inch centers, 32-inch centers, 48-inch centers? It's all information that we need to know. Another test is borescopes. So that 3/8 hole we drilled, you can push a borescope in there, look around, look for corrosion, look for what kind of anchors type. It's real good to look in between. The cavity between the veneer and the CMU block. We're curious what's in there, what kind of anchors. Is it wet? Is it You hope it's not full. You don't know. You can measure it. So a borescopes are pretty cheap. You can buy a borescope now for $200 at Lowe's. It's not a real good one. Real good ones are multi-$1,000, but for a quick test, that'd be okay. All right, we'll talk about some load testing of existing structures. This is a common test to verify the tensile strength of a post-installed anchor. So you use a calibrated pump ram gauge system. You actually measure the force to pull an anchor out. There's 3 failure modes. The anchor will pull out. If it's the wedge anchor, maybe the mechanism failed, epoxy might have failed. So the anchor could pull out. The second one is it could be a substrate rupture or a cone fracture, like when you pull out on concrete, when it's the substrate fails, it's at a 45-degree cone failure. Or the third is the anchor would yield. It actually thin and break, which is very rare. I don't think I've ever known of that happening. So the picture on the left actually shows a cone failure. So this is us testing some fall protection anchors in masonry, and it's important that when we test these, if you look at the base of our testing apparatus, it's wide, because you don't want to be, if you test right next to the anchor, you're supporting the substrate, and so you can't get that cone fracture if that should occur. So we'll talk about some non-destructive testing methods. And so just to review, NDT, it's a testing technique. It evaluates a specific material property. It leaves the material unchanged, and the component can remain in service if acceptable. And so this is what we do with NDT equipment. We're inciting a pulse. We're sending a sound wave or radioactive waves, electromagnetic waves, magnetic waves. We're sending a pulse through the material and then capturing the return signal, or maybe capturing on the other side. But with that signal, the difference in signal, we can determine important material properties of the component we test. So it's also called NDE, in more of a research environment. They call it non-destructive evaluation, but it's using the same tools. So the most prevalent tool, non-destructive tool, is our eyes, visual inspection. And so it's the cheapest, probably most effective tool we have. When you go to a building, first thing you do, you walk around, you look for cracks, you look at the control joints, you look for obvious surface defects. To help with that it's been a big help for using drones for elevated evaluations and inspections, like cornice inspections or different masonry inspections. So the drone allows a bird's eye view without, for a lot of times we had mirrors on end of sticks, and we were hanging over trying to do what we can and tapping with hammers. And so drones really help, but drones don't tap, so you don't get an audible. And it's kind of hard if you're just looking at a wall with a drone straight on. It's hard to assess the displacement. Something might be out a half inch, but you can't really see it unless you go to the end and shoot down. So like the picture on the right would actually show you get to the end and you look down to look for displacements. So if it's commercial work, your drone operator has to be licensed. But there's actually services now. You can hire a drone company. They'll come out and they probably don't know what they're looking at, but they'll scan the building for you. All right, first NDT tool we're going to talk about is the Schmidt rebound hammer. These have been around a long time. They're invented in 1948 by Swiss engineer Ernest Schmidt. And Schmidt still makes these out of Switzerland, and they're really good. They're high quality. So you got to watch these, because you can go on eBay and buy a hammer for $160 and you don't want to use it. It's no good. So if you do invest in a rebound hammer, they're under $1,000, but get a high quality one. And so it uses the principle of the hardness of concrete by the rebound principle. It's a spring-loaded hammer. You push it against a wall, and it fires. And so it releases a spring, hits the concrete, and it bounces back. And when it bounces back, it moves a key to a number, and then you get that. So like weak concrete, like you hit it, it would be a 20. Strong concrete would be like a 40. Real strong concrete would be a 50. It's governed by C805, well-established test. So this is kind of the procedure. What you do, the first thing you do is when you come up to a sample, this is more of a concrete test, but there is a masonry unit I'll show in a minute. But so it comes with a pumice stone, and so you would actually grind your test area. You get about 2 or 3 inch diameter, and you grind that, you get away any lateness, any of that powdery dust, a little milky surface film. You get that off, so you just see your sand in your aggregate, and then you strike that area 10 times with your hammer, collect the data each time, you average that, throw out highs and lows, and then you take that number to the compressive chart, which is on the hammer. It's really, really convenient. Roll it over, and you can do it. And so on this particular one, like say your average was a 40, you go up, over to the left. So rebound number 40 is equivalent to like 5,000 PSI on the B scale. So gravity affects these. And so if you're doing it on a wall, you go to B scale. If you're doing it flat, you use A scale. Overhead would be C. Get a drink. So here's an example of a lightweight rebound hammer. This is for materials under 800 PSI. And you can do early strength concrete, like maturity testing, to determine mortar joints, gypsum plastered, lightweight material. Another test is a Windsor probe. It's kind of an old school test where you open it up, you put in a 20 caliber shot, you put a steel pin, you actually fire a steel pin into the surface of concrete. And there's tools so it lines you up. And so the depth of as the probe is fired in the concrete, the exposed length is measured. And it's a revision, penetration versus concrete strength, because so soft concrete, it's going to penetrate deeper. Hard concrete, the penetration won't be as much. There's a way you can test 3 of them and put that, take an average of the 3. And so the Windsor probe in the rebound hammer, the accuracy on that is like plus or minus 15%. It's not a hard, you can't guarantee what it is, but it's pretty close. But like the rebound hammer, it's a very good tool to compare elements. So if you've got 30 columns, you can test all 30 of them, and you can determine which one's weaker than the other. It's a very good test for fire damage concrete. So you test areas away from the fire, you get your control, this concrete's got a rebound number of 45, we're away from the fire. Then you move to the fire, and you might, it starts getting lower, and then all of a sudden you're getting a rebound number of 20, you know that concrete would be affected by a fire. So the current tools used to detect reinforcing steel is, mentioned 3 of them here. One on the left is an electromagnetic tachometer. It's based on magnetics. It's a sophisticated metal detector with a very narrow focus on it. Pretty good for detecting tendons or rebar and tendons to about depth of 5 inches. They're getting harder to find. They kind of stopped making those. Now they've kind of moved towards what these eddy current devices, profimeters. They only go about 3 or 4 inches, but it's kind of the new technology that came out. But what I can say is the best technology is actually surface penetrating radar, a unit like on the right here. So this is just its GPR. It's ground penetrating radar at a higher frequency, where GPR is, you know, they drag the cooler size antennas around in fields, and so that'll GPR finds underground tanks, pipelines and stuff. So now they perfected this, a higher frequency, so you can actually scan a slab or a wall, and what the SPR, it'll find reinforcing steel, tendons, and it also finds electrical conduit, where the two on the left, the tachometer and the eddy current, they don't find live electrical currents, where radar will, because radar works the difference in dielectric constants, and like a hollow conduit with a live wire, that looks different than steel or concrete. So through system integration, you can take one of these units, you actually have a mat, and so you do a series of tests, it collects all the data, and it will draw you a real nice image of where your tendons and your reinforcing steel is at. I can say that, like on the radar units, cheap radar units are not very good. The good ones, like a $2,000 radar unit, it's not going to work very well, but they're expensive. They're $10,000 or $15,000, $20,000, but they really do a good job. So another non-destructive tool, we'll talk about sounding, a tap test. And so we've all done this. You can learn a lot with your ear. It's, you know, the sound of the strike can indicate an area of interest. I don't know if you've ever chain dragged parking garages or bridge decks. It's an effective tool where, you know, the lamination is going to give you a lower frequency, a drumming type sound. And so you have a paint can in one and your chains in the other, and you sweep. And as you sweep, when you hear the drumming sound, you can spray it, and so you can accurately delineate the dimensions of a delamination using chain drag method or tapping. So we did this test trying to figure out, was a masonry cell grouted? I couldn't hear it with my ears. Younger person, maybe they could, but it's a tap test. So this is another tool, ultrasonic pulse velocity. This is a tool in the specifications. You've read it, where if your concrete cylinders don't make the strength, it says, and test with non-destructive, it says either use core drilling, rebound hammer, or sonoscope. So this is the sonoscope what they're talking about. And I actually have two pictures here. Picture on the left is a unit that I used about 25 years ago. And this was a robust unit. This thing would it would fire a sound wave through concrete 12 foot. It was powerful, had all sorts of buttons, you could fine tune it, and it was a great unit, but it outlived its useful life. It's dead, no one would service it. So you buy the new one over to the right, it's, you know, 1/3 the size and 1/3 the power. And so what I've kind of found with new instruments, you know, they start making them for the masses. They take all the fine tuning out of it. They're not as powerful. You know, that's why we watch eBay and we try to find some of those old units. So some of the old units were really good. So this is the principle of, it's a pulse and receiving. So you got a transducer that it pulses through the material and you capture it. So every material has an intrinsic velocity. So we know what the velocity of uncracked brickwork through empirical data and lots of laboratory testing and field data, we've established these velocities. And so we know what velocity of good concrete, bad concrete. We know the velocity of steel. So the idea when we test, so we're actually sending a sound wave, and you can learn a whole lot by sending sound waves through material. You can approximate its strength based on velocity. You do void detection. Picture on the right shows so as the sound is traveling through a part, if there's a void, now the sound has to go around the void, so it's going to take longer. So these instruments, what I'm showing, these are just kind of stopwatches. On the left, it shows 17.7 microseconds. That's the time it took for the sound to travel from the pulsar to the receiver. And so it's a comparison test. And so here's another, is this CMU wall grouted? This is where you would actually send a sound wave, and we've done this a few times. You got to have long, because one guy's got to have real long coaxial, because he's got to be on the outside of the wall. So you can shoot the sound wave across. And so a grouted cell is going to have a faster velocity, a shorter transient time. An ungrouted cell, sound's got to travel around, so it's going to be longer. So here's an application we were testing, these big fan foundations that are, they just vibrate, and they were full of exterior delaminations. They wanted to know the interior, what was the condition of the inside of the concrete. So we did a series of pulse velocity tests. It's a comparison test. We go to a good area, we get a control, and we do a series of tests through it and can locate areas of micro cracking, of voids, of delaminations, or just in general weak concrete. So the latest tool that we've been using is ultrasonic tomography, and this is a system. It's got 48 transducers. I'm going to jump to the next slide. So there's actually 48 transducers on the back of this, and they're dry point transducers. You don't need coupling. So you hold this unit against a wall. It's got a trigger fire on your thumbs. So you actually, when you fire it, it's throwing 48 sound waves into the wall. And so when one transducer fires, they all listen. When the second transducer fires, they all listen. And so through software programming, full matrix capture, what they call, it computes a 3D image, a 2D or 3D image of your test specimen. So this is an area, this is that same sound foundation, fan foundation. We're trying to figure out the interior. So you can shoot about 4 foot with this unit. You actually go all the way through. And so what the pictures on the right, the red indicates reinforcing steel. So it shows we have 4 vertical reinforcing steels, 1 horizontal bar there. And so how this differs from GPR though is this measures the shear velocity. And we said, with shear velocity, we can estimate the strength of the concrete. With GPR or SPR before, that shows you where the rebar is, but there tells you nothing about strength. And also, this is good for finding defects in the concrete where radar really doesn't. So this is a good tool for detecting internal damage, measuring the shear velocity. So here's a recent job where these very critical walls, 20 inches thick, and there's one area, and there was several areas in particular that had honeycomb. The mix was poured too dry. The reinforcing steel didn't have adequate clearance. So when they pulled the forms, 99% of the wall was beautiful, nice, slick, looked good, but 1%, and these are big walls, showed honeycomb. So the owner, was like, how do we know that defect doesn't go all the way through the wall? So using the tomography, it's a system. The top right picture shows, like, we took 15 different shots within that yellow box, and then through, it's a quick test. Within 3 minutes or 4 minutes, you can draw the 2D image, and then you hook it to a computer, and it integrates it all together, so you have a 3D image of your wall structure and fast. And so what this is telling us is the red is rebar, the yellow would be weakened concrete matrix, so honeycomb, blue is sound concrete. And then at the very bottom, the bottom left picture, there's like 4 lighter blue. That actually shows the backside of the concrete. So you can measure the thickness plus or minus an inch with this unit also. Talk about infrared thermography. This is a great tool with multiple uses. And so this is an application to find is that wall grouted? Is it reinforced? And so the idea with infrared thermography, you use your sun as your energy source. So it induces a uniform heat pattern on a wall during the daytime. So it's uniformly heated up when it cools off at night. So infrared thermography, you go out at 6 or 7 o'clock at night, as the wall is cooling off, thin areas cool faster than thick areas. And so you scan it with the infrared thermography gun, and which used to be very expensive, and now you can get a good gun under $10,000, a good camera. And so you can, one of the uses is to determine if the cells are grouted or not. This example, the picture on the right, that black box, so the yellow line is actually, it's warmer, so a grouted cell is warmer because it's thick. The thin sections would be the ungrouted portions. Another application for infrared thermography, another civil application, is determining roof deck or moisture under roof decks. The same thing. So this is go up on a roof deck. In the daytime, the sun emits a uniform heat pattern on the slab. When the sun goes down, it starts cooling off. A wet area is gonna retain heat longer than the dry area. So the yellow and red areas, those are hotter than the blue areas. So you know where there's a leak somewhere in that area, and that's the insulation that would have to be replaced. On the right, it's a bridge deck, same principle. Sun heats it up. A cooler area that's delaminated will cool faster than a full slab. All right, so got a couple demolition videos here. So, knowing material properties allows a safe demolition of a structure. So we know the geometry, we study the connections, and we do enough testing to determine material properties. So this is a demo of a coal-fired power plant smokestack. If you look at the little crown at the top, the masonry crown disconnects. The steel sleeve stopped at that elevation. All right, here's a view of a reinforced concrete shell from above. There's no sound on this one. How it folds over, interesting. Here's another rear view of a stack. There's a lot of skill in making it fall in the right direction. Because you're usually next to a building and a river. You don't want to hit either one. So, and last but not least, 4 of them. All right, so that is the end of my presentation.
Fantastic. Does anybody have any questions? No questions?